Hi everyone, this video is the solution to example 3 of B moment distribution. So the first thing we have to do is to lock all indeterminate nodes. Again, B is an indeterminate node because we don't know its moment of rotation, while C, we're going to lock it as well, but just for a little bit, because we know that the moment at C has to be 20 times 5, because we can calculate the moment from the right side of the structure. So the first step is to get our fixed end moments. So here we have a case of a fixed beam with a UDL, and we have also the case of a fixed beam with a load that it's not centered. So for the UDL, we know the moments are WL squared divided by 12, which in this case is 10 times 20 squared divided by 12, which is equal to 333.3. Now for the case of the load that is not centered, on the left side and the right side we have different moments, so let's do moment in the left, that's equal to FAB squared divided by L squared, and the moment on the right is equal to FA squared B divided by L squared. In this case, A is our 10 meters and B is our 15 meters. So for the moment of the left, we're going to do 50 times 10 times 15 squared divided by 25 squared. So you get 180. For the moment of the right, we just change the square, so it's going to be 50 times 10 squared times 15 divided by 25 squared, and we get 120. Okay, that concludes our fixed end moments. We can now go to distribution factors. And now, since we only have B as the indeterminate node, we only need to do it for node B. So we need to consider bar AB, and we need to consider bar BC. And the stiffness for AB is 4EI over L, since it's fixed. In this case, L is 20. And then for BC, we're not considering C to be fixed, so we're considering 3EI over 25, which now means the distribution factor of AB and BC are equal to 4EI over 20 divided by the sum of the two, and then for BC is the same, but now with the stiffness of BC in the numerator. Again, the EI simplify, so we can do this quickly. So in this case, we have 5 over 8 for AB and then 3 over 8 for BC. So we're going to skip the step of defining the carryover factors, and we do it straight in the balancing of the structure. So to balance the structure, we draw our structure very carefully. Remember, we have a little bit of a cantilever, and then we're going to start adding our distribution factors here. So we get 3 over 8 on the right side, and we get 5 over 8 on the left. Now the carryover factors, we know it's 0.5 between fixed supports, and again remember that B is assumed to be fixed, and then between the pin and the fixed, it only works in the direction of the fixed. So this is our carryover factors. We can now write down our fixed end moments. Let's just have a look there. So on the left is 333.3, here as well, and here we get 180 on the left and then 120 on the right. As usual, on the left is negative, and then on the right it stays positive. So now, what's the secret for this problem in particular? We have a bit of the structure that is cantilevered. So we know that the moment at C has to be 20 times 5. So the moment at C has to be 100. And we know that from the get-go. So what we're going to see is that if we have 120 and we want to make it equal to 100, we have to go and subtract 20. And here we get our final moment. That is the one we need for that specific node C. So, and then we continue as usual. If we apply minus 20, we need to transfer half, so minus 10. And then we can add and get our minus 190. That will need to be compared in the next iteration with this 333.3. Now, since we only have one indeterminate node, unlike the last example, we have to do this just once. So we have 333.3 minus 190. So the difference is 143.3. And we know the negatives are losing, so we need to apply negative moments. So I'm going to do 143.3 times 5 over 8, and I get 89.6. So I'm going to apply here minus 89.6. And if I do 143.3 times 3 over 8, I do 53.7, also negative. And here we need to check straight away that we didn't do any mistake in the calculation. 333.3 minus 89.6 gives me 243.7. And then on this side, if you do 190 plus 53.7, we get negative, in this case, 243.7. So that means everything is working fine. Now the last step is to transfer half to this side. So 89.6 divided by 2 is 44.8, also negative. So then we can add and get our final answer. That's 378.1. Okay, so now we're done with balancing the structure. It's a lot faster than the previous one. The next step is to get our free end moments. And in this case, we have to consider only bar AB that has a UDL. And we need to consider bar BC that has a load that is not in the center. So we know the load is applied 10 meters from the left and then 15 meters from the right. So for the moment on the UDL, we know that it's a parabolic moment, and then the maximum is PL square over 8, or WL square over 8. And in this case, is 10 times 20 squared divided by 8, and this is equal to 500. In the case of bar BC, the moment will have a maximum underneath the load, but first we need to calculate these reactions. So we know that 50 times 10 has to be this reaction times 25. So we're going to do 50 times 10 divided by 25, and this gives us the reaction on the right. And if you want to do 50 times 15 divided by 25, and you get the reaction on the left, okay? Which kind of makes sense. If you have 30 on the left, makes sense because the 50 is closer to the left than to the right. So now, if we want to know the moment here, we can either do 30 times 10 or 20 times 15, and we get the moment here is 300. Okay, now we're in a situation to do the bending moment diagram. I'm going to do it here on the side. And as usual, we're going to draw a big structure here. Know that we have our support here, another support here, and a fixed support. We can start adding the moments at the supports from the balancing table. So we know we have 378.1 on the left. Here you can see that there's a little mistake on the balancing table. There's a minus sign missing there. And because it's the left, we don't change the sign, so we stay with the minus. And here 243.7, on the right we change the sign, and we can see from the other one that should be negative, so to 243.7. And we know here on the right side plus 100, we need to change it to minus 100. So tension on the top side. So this is our moments from the balancing table. So now we add a parabola for this part of the structure, and then we add a triangle here, again 10 meters to the left, 15 to the right, so something that looks like this. And then the last part we can connect straight down to 0 because it's the end of our structure. So this part is negative, this is now as well, and this as well. And now the only thing we need to do is to define those positive moments. So here in the middle we're assuming 500, so it's 500 minus, and now we're getting the average between these two. So here the average is 310.9. So we're going to subtract from the 500, 310.9, and this gives us the moment 189.1. And here underneath the load, so at the distance of 10 meters from the support, we have a moment of 300, and we're going to subtract the value that is located underneath this load, so it's 10 meters from the support. So in this case, what we're going to do is find the difference between these two. So 243.7 minus 100. This gives me 143.7. If I divide this by the length, in this case 25 meters, so this total length is 25, I'm going to get the slope of that line. So if I divide by 25, I get a slope of 5.75. So this slope is 5.75. So if I want to know the value here, 10 meters from the support, I'm just going to do 243.7 minus 5.75 times 10. And this gives me 186.2. That's the value at 10 meters, 186.2. and this is what I need to subtract from the 300. This gives me 113.8. And that's it. That concludes the bending moment diagram here. Now let's go straight into the deflection, and then we do the shear force underneath. So to sketch the deflection, we're going to use the bending moment diagram again. We have a support here, and a fixed support here. And now by this stage you should start getting better at sketching this type of things. So here we have a no rotation, no displacement, then it starts curving down, then it starts curving up again, then starts curving down again, then up, then down. And here you can see the moment is always negative, so that means the curvature still keeps tension on the top, okay? So always an unhappy beam. So this is the way you can sketch your deflection in a quick way. Even if the problem looks complicated, the deflection can always be done quick. Okay, final step is to get the shear force diagram. Here we need to draw our bars again. So we know we have a UDL of 10 in a span of 20. So that gives us 10 times 20 is 200. So we know that the left reaction has to be 100 and the right reaction is 100. But now on top of this we have some moments. So we have 378.1 and 243.7. So here 378.1, 243.7. And now we can see that 378 is bigger, so we need to add a moment that counteracts this one. So we need reaction to go down here and up here, so it adds to this type of moment. Now we're going to do the difference of the two, 378 minus 243.7, and then we're going to divide by 20, and we get our reaction. So here we get 134.4, that's the difference, divided by 20. Gives me 672, which is the force I need to balance the moments. So now I can add them up, and here I get 106.72, and on the other side I get 93.3. Both of them up. For the other bar, we have our 50 here. We already know the reactions from the free-ended moment, so we know it's 30 and 20. And now we're just going to add the moments. We have 100 on the right, and on the left we get 243.7. So again, the 243 is bigger, so we need to balance with a clockwise rotation, and our difference here is 143.7 that we're going to divide by the total length, which is 25. And here we get 575 for these two forces. When we add up, we get 35.75, and here we get 14.25. Okay, this looks good. And now we can draw our diagram and get our reactions. So we get 106.72. Here we get 93.3. Here we get 35.75. Here we get 14.25. And the shear force here, we can check straight away from the right side. And we go, no, this 20 has to be closed at point D. So we know that at point C, we have to start at 20, and then at D, this will close at 0. So then the only thing we need to do here is consider that at AB we have a UDL, so it's just a straight line. And then here we can do our shear force like this, because we know there's a load of 50 after 10 meters, okay? Now, then these are positive shear forces, these are negative shear forces, and this is how the diagram would look. In terms of reactions, this will be 106.7. The reaction here is 93.3 plus 35.75. That's 129.05. And here the reaction is 34.25. This concludes this solution to this problem. Thank you for watching, and have a good day.